in 126, we constantly used the right-hand rule for many different things. So I want to go over when to use it and how to use it. There's really two reasons to use the right-hand rule. The first is when you have cross products. Anytime we have the mathematical formula where you have to combine two vectors like A cross B equals C. So to do this, we have one way where you put your fingers along A, and then you make your wrists so that you can curve them to B. So that's this motion we're always doing. A cross B, or maybe A, if B is now that way, we can't have our wrist this way, we have to go that way, B. And then your thumb is the answer, the C vector. So this is what we did when we said the force on a charge moving in a magnetic field is QV cross B. So we put our fingers along V, and we turn our wrist until we can curl it toward B. And then your thumb is the direction of the force. The other magnetic force is really pretty much the same thing for a current, L cross B. And it's really the same because this is basically the same. Instead of individual charges moving at V, we think of the flow of charge along the wire in the direction L. Again, your fingers go along L and you turn them towards B. Another way to do it is to just hold your hand into a roll of right-handed coordinate system. And then it's pointer finger crossed with tall man, and the answer is in the direction of your thumb. So this would be pointer, and then this is tall man. And then this, again, your thumb is the answer. And pointer and tall man don't actually have to be at exactly 90. If the angle varies, you just vary the angle between those two. But the point is they make a plane. And if you put this the first vector and this the second vector, your thumb will always be the direction of the answer. So let's do a couple real quick. So there's a B field to the right, and there is a positive charge moving that way. So if we're going to use this method, then fingers along V, I'm going to come over here. And if I put my fingers along V like that, they wouldn't curve towards B, would they? They would curve into the board. And B is to the right. So you got to figure out how to turn your wrist where V is this way. And now if I turn them towards B. Even though they are at 90 degrees, that's still turning it towards B. Fingers along V, turn towards B, and my thumb is out. So the force must be out. If in this I had a wire with current going up, then I would take the length of wire, I put my fingers up, and this isn't right, B is not this way, B is that way. So I L, my fingers along L, cross to B. The force on that wire would be M. And of course the other types are when the field is into the board, like that. So say I had a positive charge moving down. In this case, V is now in. So V cross B, the force is to the right. Let's do this method. Let's see, for this one, I get this along V, and then I need this one to be B. There we go. V and B. My thumb is out. And then here, finger along I, and I want to get, finger along I, tall man, or pointer along I, tall man along B, it's in. And then down here, pointer along V, pointer along that, pointer along V, tall man in. I'm going to break my wrist. Wait. Pointer along V, tall man in. Yes, there's my thumb going this way. Ow. Okay, so that's how you do all of those. And you've done that a few times. I think the question is really more on the second use. because this is sort of a mathematical standard. This is how we always do it. But then, part 2 is everything else. So it's what I've said is anytime one thing is straight and one thing is curving, you can apply the right-hand rule. So let's look at it this way. So here is the example. I think I have 11. And then here is the straight part, which you do with your thumb. And then here is the curvy part, which you do with your fingers. All right, and then we'll draw it over to the side. And we'll see all the ones I could think of. Let's start with just a wire. Remember, anytime you have a wire, we're applying that the wire is carrying current. So if you have a wire like this, current, and for these you also kind of have to know what's going to happen. You have to know that there's a straight part and a curvy part. You have to know that around the wire, the field makes little circles around the wire. So clearly the straight part is the wire. And the curvy part is the B field. And this is telling you, put your thumb along the straight part. And then the field will do what your fingers are doing. They go into the board and come out around like that. So now we know the field goes like this. Around the front of the wire and up the back of the wire. So that's one. Let's do a wire loop. Wire loop. Well, in a wire loop like this, right? So the thick part is in the front of the drawing here, and we're going to have the current going around like that. And the B field you want from a wire loop is here in the center. So you may recall or know that the B field is straight, perpendicular to the wire loop. So let's see, what's straight? The B field. The B, and here we're talking at the center. And what's curvy is the wire. So right hand, fingers going around the curve, the wire, like from the front to the back. Oh, the B field must be that way. Right. Curvy, straight. All right. Well, I have 7. I better start writing smaller. Let's do a wire loop around the edge. So we don't want the center. So let me show you what I mean by that. Is here's the front of the wire loop, just like before. That's the front. The current's going towards the back, just like that. But we can actually go anywhere on the wire and treat it like one of these. So then the straight part is the wire, and here is the B, we'll say at the edge. Okay? The B at the edge, so if we're on the front, I'm going to put my fingers along the front of the curve, and I'm going to find it looks just like that. Right? The B field is going to come up on the inside and go out on the back. And here it's going like this, also up. And if I fall around to the back, then it's going behind the wire and up in the middle, right? Like that. And then you can start to recognize that everywhere you go, here the wire is coming out of the board, up. The edge field goes up, and it goes down as you go through like that. Everywhere you go, the B field is swirling where it's going up in the middle. That on the inside of the wire, the B field is always up. Well, that makes sense because that all adds up, and the same thing happens in the center. So it's the same answer, but you could kind of get there with either one of these. You could tell that if the current goes that way, the B field is up in the center. Either with this rule or find this rule all the way around the edge. It always works. Let's keep going. I also came up with the solenoid. I mean, I didn't come up with it. It's been around for a very long time. The solenoid is kind of like this. Okay, so if current is flowing through the solenoid, what is straight is the B field, because the solenoid makes a uniform magnetic field in the center, and what is curvy is the current. Now in a drawing like that, it's a little hard to interpret which way it's curving, unless I get real specific about which side of the loop's on the front, but whatever, let's say it's going around like this. I think I meant for it to go around like that, where this is the front and that's the back. B field is down. And I got the direction because I know that my finger is curved with the current. And the B field is my thumb. Oh, we're not done. What else we have? Area. Just the concept of turning area into a vector. Well, the curvy thing is the positive direction around the loop. And the straight thing is the area vector. So let's draw it and say, let's see, so if I have a little disc like that, it's sticking out in the front as always. And if I had the not the current, but just I've defined this way as positive, out and then into the board. If that's positive, then the area vector sticks up. If you're looking down, that would be counterclockwise. Then went the other way, the area vector would stick down. It's up to you which way the area vector goes. Let's see, that's 1, 2, 3, 4, 5. We've got 2 more. I think I'll erase the top 2. We'll keep going. What else we got here? The magnetic moment. We didn't talk about it too much, just at the end, the magnetic moment mu. And for mu, remember you had a current going in a loop. So this is outside of the board, and the current going around like that. Which way is mu? Well, the current is going around in circles, and the straight is the vector mu. So here, this is coming out of the board like that. Mu is this way. And I have one more. The last one I could think of. Maybe there's others. I mean, there's many others, but maybe there's others that are important. I'm going to call it torque and rotation. Okay, so you can think of those problems we had where we had a wire square loop in a magnetic field, and we thought about the forces on it, and we said, oh yeah, it comes out this way, and it goes in that way. That means the force is out of the board here, and it's into the board there, and we said that'll cause a torque. In this case, I'm going to go that way. We could also do the calculations to get the torque down. So which way is that going to rotate? So there's a relationship between the torque and the direction it tends to make it rotate. We'll go the torque is straight, and this is the rotation. So if we see a torque down like this, thumb down, we know it's going to rotate like that. We could have gotten the torque vector itself from the right-hand rule. The torque is mu cross B. But here I was just thinking back to when we just thought about which way the force is. You could also get the torque from the R cross F. As you know, R from the axis rotation over the forces applied. Right, so that's 7. That's about all I could think of. Examples when we just use these sort of everyday right-hand rules that help you find the direction